Hi everyone! Today I will walk you through a complete skin cancer detection project using deep learning, where we process skin lesion images, train CNN models like DenseNet 121 and EfficientNet B4, evaluate performance, and save the trained models for real-world testing. This project helps automate early detection of skin cancer by teaching models to classify lesion images, which can speed up diagnosis, assist doctors, and potentially improve patient outcomes. To get this project, go to Google and search Skin Cancer Detection using Deep Learning Online course. Click the course result, look for the AI online course, and you'll find the full project and dataset with step-by-step instructions inside the course. Now, I'll explain all the project code line by line, so anyone can understand how it works. Let's go. Here, mounting Google Drive. Here, we are installing all necessary libraries, such as LangChain, Face, Transformers. Importing libraries. Here, we import all the essential libraries that will handle every major step of our workflow, starting from processing and preparing the image data, to building and training our deep learning model, and finally evaluating the results with clear metrics and visualizations. Load datasets. Set the main dataset path stored in Google Drive. Then we create separate paths for the training and validation folders by joining the base dataset directory with their respective subfolders. Listing categories. The image size is set to 128 for pre-processing purposes. All folder names inside the training directory are collected and stored in the categories list. The final list is printed to show the available labels in the training dataset. Data processing. We read each image from every class folder, resize it to the defined size, and store it along with its corresponding label. We also count how many images belong to each class, and return both the processed data and the class counts. Next, process the training data and print the total number of training samples. The output shows the final count, confirming how many training samples were successfully processed. Plotting class distributions. We plot a bar chart showing the number of images in each category of the training dataset. The bars are colored using a Voridus color map, and labels, title, and proper rotation are added for clear visualization. Process the validation data and print the total number of validation samples. Here, the output displays the total count, confirming how many validation samples were successfully processed. Plotting validation data distribution. We plot a bar chart to show the number of images in each category of the validation dataset. The bars are colored using a Voridus color map with labels, title, and rotated x-axis ticks for clear visualization. Preparing data for model. Images and labels from the training data are separated, converted into numerical Python arrays with the correct shape and type, and their dimensions are printed. Validation images and labels are separated, converted into properly shaped numerical Python arrays, printed for their dimensions, and both training and test images are normalized by dividing by 255. Visualizing random training images. We select one random image from each category in the training dataset and store their paths. These images are then displayed in a 3x3 grid with their category names as titles for easy visualization. Building a basic CNN model. For the basic CNN model, the input shape is set to match the image dimensions with 3 color channels, and the number of output classes is defined as 9. A basic CNN model is defined with 2 convolutional and max pooling layers, followed by a flattening layer and 2 dense layers for classification. The model is compiled using the Atom Optimizer and sparse categorical cross-entropy loss, and its summary is displayed. Training the basic CNN model. The model is trained on the training data with validation on the test set for 100 epochs and a batch size of 32. The model checkpoint callback saves only the weights of the model that achieve the highest validation accuracy. Plotting training history. We plot the training and validation accuracy and loss curves of the model over all epochs. This helps visualize how the model's performance improves and whether it is overfitting or underfitting. Evaluating model performance. Performance is evaluated on both the training and test datasets to obtain loss and accuracy values. The results are then printed to compare training and validation performance. Evaluating the model. The saved CNN model is loaded from the file basicCNN.h5 and evaluated on the test dataset to get loss and accuracy. The test accuracy is then printed as a percentage. Saving the DenseNet 121 model. Trained DenseNet 121 model, along with its weights, is saved to the file DenseNet 121 model.h5. Plotting confusion matrix and classification report. Next, a confusion matrix is plotted to visualize how the DenseNet 121 model's predictions compare with the actual labels. A classification report is also printed to show precision, recall, and F1 scores for each class. We use this command to install the EfficientNet library in our environment. Building our EfficientNet B4. An EfficientNet B4 based model is created using pre-trained ImageNet weights, with additional custom layers added for classification, while keeping the original layers frozen. After compiling the model with Atom and sparse categorical cross-entropy, the full architecture is displayed through the model summary. Training the EfficientNet B4. The EfficientNet B4 model is trained on the training data for 100 epochs with a batch size of 64 and validated on the test set. The training history, including accuracy and loss, is recorded for analysis. Plotting training history. Training and validation accuracy and loss curves of the EfficientNet B4 model are plotted over all epochs. This helps visualize the model's learning progress and detect overfitting or underfitting. Evaluating model performance. The EfficientNet B4 model is evaluated on both the training and test datasets to obtain loss and accuracy metrics. The results are printed to compare the model's performance on training and validation data. Evaluating the model. EfficientNet B4 model is evaluated on the test dataset to obtain its loss and accuracy. The test accuracy is then printed as a percentage. Saving the EfficientNet model. Next, we save the EfficientNet model architecture and weights. Plotting confusion matrix and classification report. A confusion matrix is plotted to show how the EfficientNet B4 model's predictions compare with the actual labels. A classification report is also printed to display precision, recall, and F1 scores for each category. Load the model EfficientNet B4. The saved EfficientNet B4 model is loaded from the file EfficientNet B4 model.h5 for evaluation or further use. Finally, we load an input image, resize and normalize it, and prepare it for prediction by the pre-trained EfficientNet B4 model. We then predict the class of the image and display it with the predicted class label as the title. This project helps detect skin cancer much faster, delivers more accurate diagnoses, and makes advanced detection accessible to everyone. If you want to explore projects like this, be sure to visit AIOnlineCourse.com for more AI-based projects.